Mr. David Hein flew all the way in from Toronto, Canada. David is the Principal Engineer and Vice President of Transportation of Applied Research Associates, Toronto, Canada. David has been extensively involved in the design, construction and management of permeable pavements. He has published 15 technical papers on permeable pavements, has given over 100 technical presentations on this subject. He's also the chair of the American Society of Civil Engineers that developed a standard for the design of interlocking concrete pavements, the municipal roadways, and another standard on the design, construction and maintenance of permeable interlocking concrete pavements. David has been extensively involved in permeable pavement systems, including the development of the Permeable Design Pro software. This is definitely something we are going to look at today, and I will just leave the field to David. Round of applause.
Thank you. Hello everyone, and very nice to be here. Just out of curiosity, how many people in here are architects, landscape architects? Okay, mostly probably. Engineers? Not too bad. Contractors, suppliers, a few of those too? Oh, okay, a bunch of those, good. Awesome. When I used to do things like this, I said, how many people in the audience are engineers? And I would be the only one. All right, that's changed certainly in my neck of the woods. There's usually 60-70% of those are engineers. The reason that being is that the first thing they teach you in Pavement Engineering 101 is to get the water away from the pavement as fast as possible. We don't want it anywhere near the pavement. And so now we're taking that and we're turning it into all of a sudden this device that we're going to use with stormwater. So I'm a pavement guy. That's what I do. I'm a civil engineer, pavement guy. I deal with materials, road construction, highways, airports, whatever they are. And so, but I'm really good at hydrology. I like water. I always did like water. So when it came to opportunity to combine the two and make the impermeable pavement actually contribute to stormwater management, I thought this is really an interesting idea. And so I've been involved in this probably more than 15 years now or so. And I've seen pretty much everything you can see about people not understanding, not wanting to do this, worried about maintenance, all this kind of stuff. And so part of my work over the past 15 years has been to help people understand, number one, how to do this, how to do it right, how to design it correctly, how to more importantly build it correctly like we design it. And that's also a challenge for some of us. And then also, all pavements need maintenance. It doesn't matter what kind of pavement you build. If you build a pavement and you never have traffic on it, it will still fall apart. So they all need maintenance at some point in time during their life. So we're not trying to build something that's going to last 50 years and we never have to touch it, because it's not possible. It's very difficult to do that. And so what I'm going to do is I'm going to talk briefly here about the integrating hydraulic and structural design using a particular software application that we developed. So I'm going to give you a bit of a presentation with slides and overview, and then I'm going to do a short run through on an actual live example of how this works. And so where this came from was back in 2008. We sat down with some of the industry and talked about the barriers to implementation. So what is stopping us from using more permeable pavements? And one of those answers, the top, we made a list of numbers. There was 25 or 30 of these things. And one of the top numbers was, or elements was, how do we actually integrate structural and hydraulic design, and how do we do that so that people can understand it? I'm a guy that hates things that are complicated. Complication is an excuse for bad design. Right? If it's complicated, people don't use it. They don't understand it, they won't use it, it won't happen. So this actually came out of that little summit that we had about barriers, and we developed this application here, which I'll talk about. And interestingly enough, in 3 weeks, we have another meeting, exactly the same thing happening in the University of California, Davis, where we're bringing together 50 of the people from North America who have been involved in permeable pavement design and construction, and we're having the exact same conversation again, because we're trying to remove the barriers to implementation. So we'll talk a little bit about this. So you've heard some of this stuff today already in terms of what a permeable pavement consists of. The surfaces can be asphalt, concrete, it can be grids, it can be paving stones, it can be brick pavements, it can be all kinds of different things. But ultimately, as Bob mentioned, the underlying materials are all open graded materials. Romans did this 2,000 years ago, and as he said, there are still actually people driving on the same roads that were built 2,000 years ago, and they're still functioning. In fact, I opened some of my presentations with a picture of the Appian Way in Rome. So bottom line, that's the pavement structure itself. Not to go into this in great detail, but there are two sides to this. In normal pavement design, I have to build a pavement that can handle the loads. And pavement design is all about loads and bending. And so when I build a pavement, I drive across it, it does this. All right? If it all went like this, it would never fail, because there's never any strain, there's never any bending happening. When a vehicle drives across it, when your vehicle, your personal passenger vehicle rides across the roadway, it don't care. Motorcycles, passenger vehicles, pickup trucks, we don't care. We don't design for them at all. This is no influence on our pavement structure. We care about buses, trucks, any other heavy vehicles. Those are the things that are pavement killers. So when it bends, it starts pulling strands at the bottom of the material and it starts to deform. Or the whole pavement goes down and doesn't come back up, and it keeps doing that, doesn't go back up, and it ruts. So we get a bowl kind of thing happening underneath the wheel load. So that's the structural design part of it. Typically when you have a permeable interlocking concrete pavement, I don't care about the bending because they're called semi-rigid pavements. They don't crack. The blocks themselves are 50, 60 MPa concrete, really, really strong. All right? What happens is they potentially can deform and rut. So we want to make sure that doesn't happen. So that's the structural design part of it. On the hydrologic side part of it, I got to get water in. Once it's in, I got to make sure it goes down. Once it goes down, I need to know whether it goes down all the way or it goes this way. So I got to control the water. I don't want it coming back up through the pavement structure. Ideally, I design a pavement that is just strong enough to handle the traffic and just thick enough to handle the water. Then it's optimal. I got a perfectly good design. And so we do a lot of things to make sure that happens. So this is basically the process that we go through to make that happen. So in terms of hydrologic design, we got to know why we're building a permeable pavement. What are my goals? Am I cleaning water? Am I reducing quantities of water? Am I delaying it from going downstream? You know, what are my goals? And I achieve those goals in different ways. So it's the first thing I ask people. You know, why are you building a permeable pavement? A lot of answers I get is, I want to be green. Okay, that's nice, you want to be green. Okay, so let's talk about where you are. And I've done one at the Arctic Circle, and I had to explain to people it doesn't rain at the Arctic Circle, and it doesn't snow at the Arctic Circle. It's a northern desert. They said, we still want a permeable pavement because we want to be green. Okay, you got crappy soil. Dig a hole 3 meters deep, 3 meters in diameter, 5 meters deep, put all the water in there, and I'll be dead before it fills up because you don't have any water. But they want to be green, so that's their goal ultimately. So there's a number of different reasons why you do this. Flood control has become a bigger issue, certainly in the U.S. particularly. They've had, I don't know how many 1 in 500 year storms in the past 10 years. You heard there's three hurricanes went through in the last couple of months, amazing amount of flooding happening. We've got entire residential subdivisions that are being reconstructed to be permeable pavements. They are the flood control equipment. That's what they do. They're actually reducing flooding in a big way. In terms of the different kinds of systems, Bob mentioned this a little bit. This is basically 3 different kinds. We're looking at full infiltration, water goes into the ground. Sandy soils, no problem. You're along the side of a river, a stream, a beach, or whatever, you're going to get water going into these pavement structures, whether it's asphalt, concrete, or pavers, or either way. When it's a partial infiltration system, we got water going in, and then we can't get it all in. It starts to build up as the storm goes on here, and I don't want it to go through the surface of the pavement, so I need to deal with it. I need to take it away. And we can design a piping system potentially, or other things to get the water out. Then we got our no infiltration system, which is basically the line system that we're using to capture the water, and we're going to use that water for gray water, toilets, laundry, feed the plants, that kind of stuff. And so we design each of these differently than each other, and that's part of what we'll talk about. So I want to divide structural analysis and hydrological analysis into 2 pieces. This is the more complicated one, and so we've got a lot of different things we can do to change stuff. Structural analysis, that basically is all the pavement strength comes from how thick and how stiff. Concrete is 20 times stiffer than asphalt, so therefore I can use less concrete than I use asphalt. Maybe I have no surface. It could be an aggregate surface as well. And so it's a little bit easier to do than doing the hydrologic side of things. So ultimately we're trying to balance all of this stuff, and that all impacts on our design, and so we have to deal with it all. How much space is between our aggregates? How much water is flowing on the surface? How much is coming from the adjacent property? How much is coming from the roof of the building? Where is this all coming from, and how do I deal with it once I get it? I have to deal with all of those items. And then ultimately, if we can, we'd like to get it into the ground, obviously. That's where it came from in the first place, and we'd like to make that happen. So back in 2008, we said, okay, let's make something simple for people. So ultimately, I'm just going to talk briefly about how this happens. So some of the things we need to know for input for design. I need to know what the permeability is of my soil below. If it's a greenfield site, I go and I dig test pits and I find out what the elevation is going to be, where my subgrade is going to be, and I want to do testing. I want to know actually what is going to be my infiltration rate at that location. This particular case is Berkeley, California. We were reconstructing a street, ripping up the old non-permeable surface and putting in a new permeable pavement. So we dug holes in the street, and we got down to where we're going to found our pavement structure, and we measured the permeability. We're always surprised that it's usually higher than we expect it's going to be. People say you can't build permeable pavements on clay. All right, 90% of North America is clay. silty clay. In some cases, really bad, fat clays and a lot of silts and glacial deposits and things like that. We have maybe 10% of the surface areas which are sandy, like around where I live or on a Great Lake, but most of our situations are clay. And so we have tons of permeable pavements in clay situations. You heard the comment earlier about 2 millimeters. It was 2 millimeters an hour of clay, some of you were talking about, right, Nick? And so 2 millimeters an hour is like 50 millimeters in 24 hours, and 50 millimeters in 24 hours is this much rain. 3 days, it's 150 millimeters. That's a lot in 72 hours, but it will infiltrate easily. All right? Usually we actually get more than that actually happening. So we dig this up, we put in permeameters in here, and we measure the permeability of the soils. And then I need to know something else about the soils themselves. And so this software I'll show you later on basically is we classify it. Give me a gradation of the material. I classify it as clay, silt, whatever the number of categories, 8 or 10 different categories are. We're looking at the gradation, what the particle sizes are, and this is input values for this software. Comes with defaults. Tells you what normally you would have if you don't know anything. And ultimately the best thing, if for preliminary design, you can use the defaults, it's fine. It's gross categories of soil types. For detailed design, we want to actually know on our particular site. So we want to find out what the permeability is. In this particular case here, this was silty clay. We expected very low permeability. The actual number we got was this, 1.64 centimeters an hour, so 10 millimeters an hour. And this was clay. So that's what we had in situ. So we enter some information. We talk about, you heard talk about CBR, California Bearing Ratio. This is a test that we use to measure the strength of the soil. This test is a surrogate for resilient modulus. Resilient modulus basically is you take a bunch of soil, you put it in a can, you squeeze it. When you squeeze it like this, it goes this way. We measure how much it squeezes out. If it doesn't squeeze a lot, high resilient modulus. If you push it down and squeeze a lot, it's a low resilient modulus. All pavement designs use only resilient modulus for design. That's what they all do. We need to know its stiffness. So when you hear things like CBR or a variety of other different things, in California use a thing called R value, they're all surrogates for resilient modulus. So what we allow you to do is, if that's what you know, you put it in the software and we convert it to resilient modulus, because that's the only thing pavement design procedures actually use. And so this ultimately is saying, well, what is the resilient modulus? We pick it, it's poorly graded sand, gives you a number here. This thing here is called a resilient modulus reduction factor, and it's a surrogate for saying, well, you know what, it's going to be wet 50% of the time of the year, so I want to reduce the strength. I want to be conservative in my strength design for my pavement structure. Then we add some things like density, some basic parameters here, and it actually calculates things like porosity. What's the open air space in the subgrade soil? What's its permeability here? And then, so we ultimately, that's what we're using as a value that says how much water is going to get into the ground. Then we also say, well, you know what? We're going to knock it down by 50% because I want to be conservative again. So I'm going to say some of that silt's going to get through the pavement structure. And in the early days where this came from, we were figuring it was going to deposit on top of the soil on the top, and it's going to reduce its permeability because it's fine stuff. And so actually we're mostly not doing that anymore. As you heard from Bob, a lot of this silt gets caught up in the grit in the surface of the pavement. So water, rainfall. So water comes down, lands on the pavement, we got to deal with it. Water can come from adjacent areas beside you. It can come from a playground, a cornfield, whatever, a non-permeable tennis court or whatever they are. And so we got to account for all the water that potentially hits this pavement surface here. And so we go and we look at things like this. This is that same road in Berkeley, California. And so we're looking at the road, which we're reconstructing, and we're looking at the sidewalk here. And we analyze the flow area around it to determine what's the total number of square meters of water that has a potential for going this way, and going this way, and coming from different sides and everywhere we go. And so I simply go and look at the concrete and go, well, 99% of the water that hits the concrete is going to land on my road. I look at the grass, and I want to know, is it really dense grass? Is it Bermuda grass? Is it what kind of grass it is? Just because it's green does not mean water gets into the grass. If you've got grass, I don't know, 100 millimeters of topsoil and clay underneath it, the majority of the water that lands in that grass is running off it. It's either going into the air or it's running off. So when you see green, don't think that means permeable, because it does not. So in this case, we had very little, very dense soil underneath it. So basically 50% of the water that landed on this grass ended up on my road. And so I have to account for those things. And how we account for those things are basically this. We need to know about what's the pavement area that we have, and then all the areas around it. We want to know how big is it. So in this case, you see numbers here of the areas of the pavement. So I would have 3 contributing areas. We have the area numbers. We have what's called a curve number, which is a curve number of 100 means all the water runs off it. Curve number of 0 means all the water goes in it. And so we classify the surfaces. We look at the roughness coefficient of the surface. If it is a smooth concrete, it's like this table, all the water is going in as fast as possible. If it's a rough surface, then the water goes slower. So I need to know that. And then I also look at the slope. If it's like this, it goes slowly. If it's like this, it goes quickly. And I look at how far does the water have to go. Why I want to know all this stuff is that I'm going to analyze this pavement in 6-minute intervals for 24 hours, 48 hours, 72 hours, whatever. And every 6 minutes, I'm going to do a water balance. Every 1/10 of an hour, I want to know where the water's coming from. So if in a really heavy part of the rainstorm, water's coming down this pavement surface really very hard, and then I've got lots of water coming from all the edges around it, I need to take care of that. And also, if it stops raining and there's no water landing here, this is still going to come and start shedding water onto the pavement, so I want to analyze that as well. It's a big water balance thing. So what I want to do then is get the water in here. So there's two things I want to make sure of. One, can it get through these joints? The joints are 9, 8, 9, 10% of the surface of the pavement. They have a grit, a chip material in those joints. Right? Water does not go through these bricks here, unless you're using the ones you saw outside here. All right? So the water doesn't go through the bricks, it goes between the joints. And sometimes the intensity of the storm is so much that the water can't get through the joints. This is very, very permeable, no problem, but I can't get the water in the first place. And it's not because the joints are clogged, it's simply because there's too much water to get in. So then it's going to pond on the surface of the pavement, or it's got to go somewhere else. And so now we design for that. So we want to make sure if the water's going to run off at the middle of the storm, where's it going to go? So we design other features to be able to handle that water, ultimately. Or, in the case of some of my friends in Texas, they actually build a parking lot with big curbs that are like this, and they expect the water to come all the way up and flood the pavement and then come down afterwards. Yeah, kind of not my favorite way of making a little detention pond there, but in huge areas we get tons of water and massive amounts of water coming in, 300, 400 millimeters of rain in cases. You want to stop it from going downstream and eroding everything else. And so they actually design parking lots to be temporary storage ponds, literally. All right, so then I look at my base material. So this, in our case, in North America, typically you put a 100 millimeter base, which is what you were talking about as your whole pavement structure. This is never more than 100 millimeters. This is big rock. This is railway ballast size stuff. So very large stone, open, and we put variety of thickness of layers basically with it. Total thickness of this, usually something between 500-600 millimeters kind of thing for our storms anyway, for fairly heavy traffic. And so we want to know about those materials again. So I want to know the gradation of the materials, and I want to know one more thing up here, because this design procedure follows what's called the American Association of State Highway and Transportation Officials, AASHTO 1993 pavement design process. And it's all about stiffness. This number is a surrogate for stiffness. 0.09 is called a layer coefficient. So we number our pavements basically, we give them strength values based on how stiff they are. So what's their modulus value. So this sub-base material here has got 0.09. Normally we would be somewhere higher than that if it's a dense graded material, but it's open. So it doesn't have the same shear capacity to have, to stop it from rutting and stuff like that. So we usually discount it a little bit because it's an open graded material. Then we've got a sub-base, same kind of deal here. We have a different gradation, and all of these are basically the defaults in the system, but you can enter all of whatever you use. You can do anything you're using in New Zealand here, and name of it whatever you want, and you basically just add things to it here, and you've got your own database of materials that are local. So that's not an issue at all. So you basically characterize those things. The bedding layer or the chip layer underneath, again, we want to know about that. One of the key things here is that we do a calculation here because we're putting this grit, this 2.6 on top of something that may be 10, 20, on top of something that may be 10 or 20, 50, 60. And I want to make sure that when I put them on top of each other, they don't fall into each other. So if I take the small grit and I put it on the big rocks and I shaked it, it's going to go right through the surface and I'm going to lose it all. So this calculation here basically goes through and tells you, are you using the right materials? Because I don't want to have the small things falling into the big rocks. So we basically grade them so that they're all going to be solid in one particular layer. So structural design. This is the strength design. And this is what's called the AASHTO design procedure. This was the standard pavement design methodology used in North America and Canada and the US since the 1960s, basically. Recently, it has been replaced with something called mechanistic empirical design, or it is being replaced. But the time the software was developed, this was the standard. So this is what we used. It has a big ugly equation on it, and it's got a whole bunch of parameters here that we need to know something about, ultimately. And so that's the last time you'll see the equation, and even when I show you the software, you won't even see that, because you don't want to know about this, right? You just want to know, what do I got to put in? And so we need to know things about traffic, all right? I mentioned motorcycles, cars, pickup trucks, don't care. I want to know about buses, trucks, whatever kind of size of trucks you've got, that kind of thing. And we want to have reasonably decent traffic. So I ask people, I design something, I ask them, what's the traffic here? They have no clue. I go out and I look at the bus stop schedule and find out how many buses a day go down this roadway. I observe how many trucks are driving down there. Is it coming to the port facility? Is it coming to, it's restricted, so there's nothing there but light vehicles. And so we need to know something about how many cars. Pavement design is not about how heavy, it's about how many. So how many different, we standardize our axle loads to 80 kilonewtons, which was from the AASHTO design procedure. So we want to calculate how many equivalent axle loads, how many times is the pavement going to bend over the next 20 years. That's what I want to know, and that's my design procedure. So we want to find out about traffic. So we go and we look, we figure out some of the stuff with this, and how many are there a day, and how many there are a year, and how many there are over the design year. Ultimately, the best is we have actual traffic counts, and many times we have no idea, so we simply guess. This is about what it is. This is a low volume road, it's going to be 50,000. This is a higher volume road, it's going to be 1 million. I don't know. So we do the best we can with traffic. And this is an extremely important pavement design procedure, and nobody ever knows the answer to it. So you want to find somebody who knows something about traffic. This is a town, city just near where I live, where they publish all of their traffic data for their city online. More and more we see many of our clients, our agencies, are all publishing actual traffic data and data that they get for design purposes. So as an engineer, I just go to their website and pull up the numbers for the area. If it's a parking lot, it's a little bit different. So this is what I want to know about. I want to know about buses, and I want to know about trucks and things like that. I'm sure you don't have that here, but there's a thing in North America where they design bridges, and it's called an H20 loading. An H20 loading is one of these. So people go to they ask, well, can I build a permeable pavement here? The agency calls the fire department and says, is this going to be okay for fire trucks? And they call it H20 loading. This is so stupid, you cannot believe how dumb this is to ask these questions. My front grass in front of my house can handle one of these. All right? It's for sitting on top of a bridge, they want to know this fire truck loading, right? But my grass in my house can handle probably 5 fire trucks driving back in front of it. There's no pavement there at all. It's not about how heavy it is, it's how many is the issue, ultimately. So there's not a permeable pavement that I've ever been involved with that couldn't handle fire trucks. I mean, this is actually not a very often load on the pavement structure. So what we do is we calculate how many axles are driving across the roadway, and this is the standard. And so the formula is, what's the actual load divided by the standard to the exponent 4. So if you have a little bit higher load, and this number becomes 90 or 100, it's a huge amount more damage. It's like 10 times the damage of your pavement because you're going up by a factor of 4. If I have a lower load like this, and I take 50 divided by 80 to the 4, every one of those 50 kilonewton loads is only 15% of the damage as one of these 80s is. And so that's why cars don't matter. The factor for your vehicle, your house vehicle, 0.00002. So just tickling it. It's like me tapping this table. I can tap this for 100 years, I'm never going to break the table. That's what your car does to the pavement structures usually. So we do this, and we figure out what kind of pavement, we have some parameters for traffic design. How many years do you want it to last? What's your annual average daily traffic here? How many vehicles are going one direction or the other, and what percentage of commercial vehicles, how heavy are the vehicles, etc. And we calculate the total number of vehicles here at the end of this design period of 20 years. I don't know, it's only cars. We pick that number will be 20,000 I think. Pick this one here, they give you 30, pick this one, it's going to give you 75. So that's if you're building a car park area, with occasional heavy vehicles, just push the default and it gives you a number. So this is an engineering educated guess. This number here, if it hits 600,000, the software puts a red flag there and says, hey, that's a lot of traffic, guys. Do you really want to design it for that kind of traffic? When it hits 1 million, it shuts itself off. It won't let you do it. All right? It literally won't let you go. Now, having said that, again, this is 2008, 2009 thoughts that we had. Since that point in time, we've learned a hell of a lot more about designing permeable pavements. I've designed permeable pavements for tanks, right? And you can do this for heavy vehicles and a lot more. And the Brits are actually doing this to 10 million easels. And we're starting to do the same thing. So, this was in the early days. We're saying, be careful, and so, make that happen. So, Then there's a couple of little safety factors. One of them is called a reliability factor. When we design pavements, that design procedure said we design it for 50% reliability, which means that if I wanted it to last 10 years, there's a 50% chance it will last 10 years, there's a chance it will last 12 or 8 or 14 or 6. There's a 50-50 chance you're going to get your 10 years. So that's not very scientific, and so they said, well, depending on how important the road or the parking lot or the street is, we may want a higher reliability. So when I go out to the Highway 1 out here, right, it's a higher importance to me, so I assign a higher reliability, like 90%, which means that 9 times out of 10, it will last at least 10 years or 20 years or what that number is. The reliability, the higher the percent reliability, the thicker the pavement gets. That's the basic premise. So this is my parking lot. I don't really worry about that. This is my major roadway, and I worry about that, so I assign a higher reliability. So basically, these are the categories of reliability that we assign for it. And most of the permeable pavements, we use something like 70 or 80% reliability at most. So then we have a thing called serviceability. It's another safety factor. It's basically about roughness. And so we have to assign some value of this for the pavement design. And where that comes into effect is basically when they did this design procedure, 5 was perfect, 0 was you can't walk on it. And so we don't build them to be 5 perfects because we never do that very, very well. So if it's a major highway or something, it will be closer to perfect because we do a lot of testing. If it is a low volume roadway, we don't do much testing. We just get what we get, and so usually it's lower. And so we actually assign a value here. In this case, we're assigning an initial serviceability of 4.5, 2.5 for when we fix it, and then these are the 2 values in terms of the smoothness factor. So those, we have to have something there, and when you see them in the software, I'll show you in a minute, we have defaults and say use this. But you can change it if you like, but we say use this. This is what we recommend. All right, so now we get an example design. 172,000 axle loads. All right, we don't design for 20 years or 10 years. We design for how much traffic. So we got 172,000 axle loads. Subgrade modulus 40 megapascals. Initial serviceability 4.1. Terminal 2.2. Reliability 70%. Our standard error, which is the other safety factor, 0.44. You drop all those numbers into that crazy equation I showed you earlier. It tells me, gives me 63 millimeters of strength. It's called the structural number. So give me 63 millimeters of strength. So how do I get 63 millimeters of strength? It's really a dimensionless number, but bottom line is I need to get this number for my design purposes. And so what we do is we say, well, first we start at the top, and our designs are usually 8 centimeter, 80 mil pavers with 50 millimeters of bedding chip, so that's 130 millimeters. So my 130 millimeters I multiply by its layer coefficient, so its strength number, its modulus number, and that's 0.3. When I do normal pavers with sand in the joints, I assign 0.42, which means it's stiffer. Because what happens is that sand in the joints is like 2 pieces of sandpaper, and I'm trying to move it, and I can't, and it won't slide by each other. Now when I open the joints and get a 6 mil or a 10 mil space in between them, it's chips, it's not sand. So the sand's not touching each other, the chips are kind of touching each other, and so it does this a little bit. And so because it does that, it's not as stiff. The paving stone is the same stiffness, it's huge. But this space between makes it not as strong, so that's why we discounted it to 0.3. So I multiply its thickness times its stiffness layer, gives me 39 millimeters. It's less than 64, so I don't have enough. I don't have enough pavement structure. Then I move along to my base. It's 100 millimeters, that's its strength. I get 9, I add 9 to 39, I get 48. Still not enough. So then what I do is I take this, I take the 63, subtract from it these 2 numbers, I calculate what I need, divide by its strength, and it says you need 275 of subgrades. So I'm done. Structural design is complete. So that's how easy it is, literally. So all of this stuff gets done for you. You don't see it. So this is actually the program. I needed 63. Here's what it does, and does the calculations of strength, and here's how it calculates the thickness of the layers. So I'll show you that live in a second here. So now I need to know about rainfall. So how much rain am I going to take care of here? What do I need to do? So just for fun, since I was coming here, we have Canada and the US in the software. I talked to Dave back there, and he helped me out here with figuring out a few things for New Zealand. And so I basically went in there and I put in a database for New Zealand for all the different districts, local areas, mostly 1 or 2 cities in different areas. And so I wanted to see, what does your rainfall look like ours? You know, is it close? Is it similar? Is it different? That kind of stuff. And then we have 2 things we need. We need to know how much rain falls for different storm return periods, basically here. And when I got the Auckland one, I almost crapped myself because I went, man, it rains a lot here. How do you guys live here? This is nuts, right? Like for us, you know, this is a lot. That's all I can say. And so then we also have a shape of the rainfall. And these are basically patterns, storm patterns, where it starts to rain really slow. This one here is like Vancouver in Canada, so it rains kind of more slowly for a while, then it speeds up a little bit and it keeps going slower. There are 4 standard rain patterns for North America. The red one is TP108, yours, right? And your storm patterns aren't substantially different than ours are, as you can see by that. So I thought that was really interesting, actually. And again, I did some goof up numbers and Dave fixed them for me, so that was thank you, Dave. And so we basically go through and look at our total different number of storm designs here, and we take the storm pattern and we distribute the rain over those elements. We then we calculate what goes in, what comes out, what goes in a pipe, all that kind of stuff, and we end up with these total amount of 24-hour rain volume, over 24 hours, how much volume of rain is for 2, 5, 10, 25, 50, 100-year storms, how much water falls on the pavement, how much water is contributing it to the pavement, what's my total water volume, ultimately to come up with our designs, and then I'll show you some of the details in a second. And so then we've got a whole bunch of other stuff. Basically it says, well, is your pavement flat? All right. If it's flat, all the water's got to go in, or it's going to come up and pond on your road, or your pavement surface. Is your pavement sloped? If your pavement sloped, some of it can run off. If it's going to run off, where's it going to go? Is it going to leave the pavement surface and go through some other cuts in the curbs and things like that? And then we have a initial depth of water above the subgrade. This means if it's raining every 3 days, right, and you don't get your water out in 72 hours, I can tell it that, you know what, for this storm, make sure you leave 50 millimeters of water in the pavement so that the next storm comes, you got 50 millimeters less capacity, so now I'm going to tell you there's a restricted zone there, right? So it's just a safety factor. And then we have a maximum allowable depth of water in the granular layer. I never like to fill my pavement full. I want to fill it no higher than the top of the base layer. I don't want it in the pavers. I want to make sure it stays below that. So it's another safety factor, basically. I don't want it coming out of the paving system, that's for sure. And then we got a whole bunch of stuff here on drainage pipes and all of the stuff that comes out. So I know what comes in, and now I know what needs to go into the ground, and I know what goes out, and how does it go there, and how does that happen. So there's a bunch of things in here like how many pipes do I need? What diameter should they be? Are they corrugated? Are they smooth? Are they on a slope? And all that stuff. And that's what we take care of that also as well. And then we've got some other little goodies here basically to talk about, once you have a pavement design, so once it goes through and runs an analysis, it will actually give you the drawing of your analysis in an exportable AutoCAD file, so you can take that, copy, paste it, change it, drop it into a design set of drawings or whatever, and you can make that happen. And you can also choose things like underdrains and membranes and geotextiles, and it draws them all into the surface, and you can use that. And then it's got some other things that says, well, number one, I want you to run this storm for 24 hours. And the next one is, but you can stop at the end of 24 hours. Next one is, keep running the analysis until there's no water in the pavement. So how long does it take all the extra water that comes from adjacent surfaces to go into the pavement, into it at the bottom, and it has to get out. So it'll say it's going to take you 63 hours to empty the pavement complete. And then there's another one that basically says, how long is it going to take to get 50% of the water out? And you can keep running that, and I'll show you an example when I go live here. All right, so that's the basics here. So here's all of the stuff about piping, here's the stuff about slope and whatnot, and I'm going to show you this thing live in a second. And then what we do is we take the design, and we have strength, and we've got water. And so ultimately what we do is we plot the 2, 5, 10, 25, 50, and 100-year design storms like this. This is the no-go zone at the top of the pavement where I said you can't put anything in there. I want it to be only 80% full. Where the 80% full line reaches this curve, it tells me that pavement we just designed is good for a return period of 50 years. Right? And so now I can change it. Now I can say, well, I don't want 50 years. I actually want 75 years. And so it'll then tell you how thick does it need to be to get to be 75 years. Oh, you didn't want to make it thicker? Well, use a bigger pipe. Or you got higher, better infiltration subgrade? Okay. Or you need stronger material? Change the material. There's a whole bunch of what ifs now. Once you've got it designed, it's really easy to change stuff. The thing that I do frequently is I take the big rocks and decide to make them a graded bunch of rocks. So not all one size. I want more strength because I got higher traffic, and I'll sacrifice permeability. Right? So there's a lot of things you can now do to change stuff to make it much easier to use. So other things that we can do. So this is what happens here. We have a design storm over 24 hours, and this is basically all of the different storms here, and the peak period is somewhere in the middle, or they usually get a lot of the rain. This is the amount of water in the base for a 2, 5, 10, 25, 50, and 100-year storm. Here's the storm starting, and it starts filling up. And then all of a sudden the storm starts to peter out, and the water starts going into the ground, and so it starts to go down again. It takes longer for the 100-year storm, obviously. This is a design that has pipes in it, so it says, you know what? when you get to a certain depth of rainfall, you know, the pipe, as Bob showed, we use the exact same weir system with the V-notch weir, and so we bury the pipes in the ground, but we then connect it to that box beside it and use that notch, the height of that V-notch weir, to determine how much water will allow in the pavement, and so we can say, you know what, start it when it gets to be 50 millimeters deep, or 100 millimeters deep, or 200 millimeters deep. And so we just change the height of the weir to govern when we decide to start taking water off the pavement, onto the pavement structure. So we control the flow of water completely. So that's this, and when you see a flat line there, it means my pipe is running full of water, completely full of water. So in this case, pretty much all of the design storms here had full pipes, which I don't like. So I make a bigger pipe. But I do want to delay it. So here's an example of a full design that says, you know what, this thing is only good for about a 3-year storm here. And so what I do is I'm going to put a pipe in there. I'm going to put in a 100 millimeter diameter pipe that's 25 millimeters off the bottom of the pavement structure, and this turned it from a 3-year to a 13-year design storm. So now I'm going to change that. I'm going to put 2 subdrains in, and they're 150 millimeter diameter. Instead, I went from that to this, to almost a 7-year design. So I can do all these what-ifs kind of things with this stuff. And everything you want to know, everything you can get out of this thing. Everything you ever want to know, all the water balance, all the calculations, everything is copy, paste, throw it into Excel. If you don't like what it does, you can do your own kind of thing. And there's stock reports that come with it that tell you you're meeting your goals and things like that. And there's all the data. You can copy, paste the data, put it wherever you want. And so ultimately, that's what was used to design this major street. From the beginning, when I showed you the permeability calculations, this is the street that was designed with that. This one also had a little weird feature because these are all grown trees here. We actually put in some bump outs around the trees to protect the roots. We actually used geocellular confinement, so there's these accordion things you pull apart and you put aggregates in it. But I also did that and then added soil to these things. The botanist guys this is Berkeley, California. You got to protect the hell out of everything, no matter what it is. And so ultimately these tree canopies were monitored over the last 5 years, and they're actually 40% bigger than they were before we put the pavement in. So there's a benefit to basically improving the tree life there for the permeable pavements. And each one of these has this little bump out thing that's got a combination of aggregate and soil. And that scares the crap out of the pavement guy, but it actually worked. And I'm going back there in about 3 weeks and I'll take more pictures. And this is, I think it's about 5 years old now. It looks perfect, absolutely gorgeous. Really, really happy about how that turned out, and so was the city. This is the software. Basically, you can go to the website and you can actually download a trial version. And Dave, you've done that as well too, right? And you had no issues. Well, you and I had some, but other than that, we fixed that, so no problem. All right, so just before I show you the quick demo, just a couple of other things that now we're going to change. This is almost 10 years old. We're going to change something based on work that's been done by the American Society of Civil Engineers. We have road people, we got water people. Water people are called EWRI, road people are called Transportation and Development Institute. So I'm the president of the Transportation and Development Institute, so I'm the road guys. So we decided to get in this is a good thing that the road guys and the water guys can all talk together. So we did that, and we produced this a couple of years ago. And so if you want to know the basics of permeable pavement design for grids, asphalt, concrete, paving stones, bricks, whatever, this is a great document. Right? It's got all the basic stuff. How do you maintain this stuff? What kind of sweepers do you need to use? All of this is all detailed in it. I was one of the editors of this thing here. Tons of checklists of all the things to do. You know, if you don't see it on the checklist, don't do it, please. You know, because we spent a lot of time thinking about how we design this stuff. So that's one thing. Second one is this. This is called this is a design standard. I chair the committee that has written this document. It's 100 pages long, and it is a guidance document for people who want to know how to design, construct, and maintain permeable pavement systems. Our committee is about 30 people, 15 pavement guys, 15 water people. We've been arguing for 4 years about what should be in this. We finally came to an agreement, and this is now being final editing, and next week it's going to be released for public comment. So people that want to go to the website can actually download and read what we've written. At the end of 45 days, basically, I do the final editing. It goes to the publication, and by January or something, this document will be out. So this is the best that we know about permeable pavement design, construction, and maintenance in North America. So if you really want to know something, and this is not just for the previous one is for I just want to know something about permeable pavements. This is saying I want to know every calculation that goes in, how we do water balance, how we do structural design, all that stuff is in this manual. So if you're an engineer, you'll like this thing for sure. It's based on, during the middle of our standard development, we said, you know what, we really don't know how long these things are going to last. You know, we tell people 15 years, 20 years, 25 years, I don't know. So there's no real design procedure for it. So the industry went through and coughed up about $400,000. This is an accelerated load machine. It's got a wheel here that goes back and forth, back and forth, back and forth. So in the middle of our standard development, we went out and did this. We went out and built some permeable pavements, and we loaded them until they failed, literally. So we decided to build 3 different sections in it, in this thing, and we rolled this wheel back and forth here. We had a lot of argument over how thick should it be. So if I built it this thick, and I put a load over it and never rutted, then I didn't learn anything. If I built it this thick and it failed in 2 days, I didn't learn anything either. So this was me that decided how thick they needed to be. So I said, oh, clearly it needs to be this, this, and this. And then I went like this and went, holy crap. You know, because I'm spending $400 grand and the thing could fail next week. You know, what am I going to do? Turned out perfect. So yeah, that's called engineering when you pull it out of your back end. So anyway, we did this, and so we built this pavement section here in Berkeley. You can see the aggregate, the big aggregate going down, and the smaller stuff on top, and the paving stones there. And we instrumented it. We put stress and strain gauges and all that kind of stuff into it. And we started loading it, and we put a bunch of loads in. We did it when it was dry, we did it when it was wet, and ultimately we put almost 1 million loads of traffic on this pavement. All right? Yep, sure.
And what was the CBR of the subgrade?
Oh, 2 point something. It was clay, California clay. It was caca. It was horrible stuff.
You put no bikes on geogrid in there?
We put a geogrid separator in the bottom. We should have actually put membrane on the side to prevent water from going sideways. We didn't do that. Hey, I'm not perfect, man. My kids think I am, but I'm not perfect. So anyway, bottom line is we tested wet and dry different cycles. So we did it separately. So when it's wet and there's water in the pavement, theoretically it's going to be less strength than if it's dry, right? So we did both. All right, then we came up with a design tool here, the Excel-based design tool for the engineer who likes everything. You can change everything you ever wanted in this and change the stiffness, change everything, change it. Is it 20 millimeters of running, 25, is it 50? What do you want to do? Blah, blah, blah. Here's your answer. So that's out there and available. And then for our standard, we came up with design tables. So we said, the important things are, how many days a year is it wet? 0 to 9, 10 to 29, whatever. Wet being defined as, how many days a year will there be water sitting in the pavement? All right, so water goes through and the aggregate's wet. When it gets to the bottom, if it goes in the ground, then that's not a wet day because it's gone. And so that was one of our criteria, because we wanted, was when it's wet, we got less loads available for it than when it was dry. So that's important to us. So you would put in whatever 100, whatever it is, how do you divide that? 120 days, or no, you said maybe 3 days? Yeah, so 120 days. So you'd be way over here someplace, 120 or more. And when it's wet, what happens is basically you need a thicker subbase. So this says, is it dry, is it wet, how many days is it wet, what kind of traffic do you have ultimately, and these tables were 25 millimeters of rutting, which we've defined as failure, how much traffic you have, and then ultimately how it works basically is you say, well, it's 50 to 89 days wet, it's going to be crappy CBR3, it's going to be 400,000 equivalent axle loads, which means I need 130 millimeters of stone and bedding layer, I need 50 millimeters of chip below it, I need 100 millimeters of base, and I need 380 millimeters of subbase. So this table is the actual one that comes into our standard. So if you're doing general design, this is more than adequate. You just pick a number from the table. You don't have to worry about doing all the calculations and all the other stuff that I showed you back here with this thing here. All right, so having said that, that is now going in there. And so we're going to have it as a secondary pavement design process because it is, we validated it, we loaded it, we made, we're really happy with this. It shows actually thinner pavement structures than what we had originally expected from the AASHTO design, which is what we thought we were going to get. So we've proven that. The other thing that was really important that we learned is that more than 500 millimeters of aggregate, there's no stress on the subgrade at all, which is really weird because when I design a pavement and I've got big rocks and middle rocks and small rocks, right? What happens when I load it and it shears and it doesn't come back, I get rutting that stays there, and so eventually my whole pavement ruts. What we get with this aggregate layer is that it's like stones touching each other, and when you load it, it goes down, but it kind of springs back. And I've seen this, never been able to prove it till now. So the bottom line is more than 50 centimeters of pavement, the subgrade, I don't care what it is. It can be sand, rock, it can be clay, it can be loon crap, right? Bottom line is there's no stress. What happens is the aggregate layer in between consolidates. So this light bulb goes off saying the most important thing we can possibly do is get good compaction of our aggregate layers. That was number one important. So that's the thing I learned out of this particular rod. So with that, I think we're finished that. Heavy vehicle loads. Having said all of that, this is called the Battle Command Center in Colorado Springs, Colorado. I was the designer of record for this. First they said they wanted it designed for like army trucks, and they came back and said they wanted Bradley vehicles, and we did the designs, and they came back and said, I want it to be good enough to handle a M1A1 Abrams main battle tank. Can you design it, Hein? And I went, yeah, but I ain't putting my stamp on that. I'm not gonna, not a chance. And so we built the test section, we drove tanks around it, we did everything you possibly could imagine. We put spikes into this, in between the holes in this pavement, we drove the tanks over it, they bent the spike like this, picked out the spike, kicked some of the grit back in, and pavements fit fine. They've now built 4 of these around the United States. So, and I believe anything can be designed. Nobody can tell me I can't do something. I'm a very, you know, you got to think outside the box sometimes, but design is, you know, you need to think outside the box and not just follow some bloody tables and stuff like that. So that's my personal opinion. This is the Olympic Village in Vancouver. This is where they said they would not get my permeable pavement dirty, and that's what it looked like during construction. So I made them rip it out. So I told them they wouldn't listen. All right. So really quickly, how much time do I have? Can I do here? Very little.
Just 10 minutes.
Okay, 10 minutes. I got it. 10 minutes. You got it. Just to give you a flavor for this. All right. So I'm going to have to change this. There we go. All right, so this is the software. Just to give you a quick flavor of what's in it. We have a hierarchical structure here. Basically, I have all of the major components here: the pavement structure, the structural design, the precipitation, and analysis. These things just basically open everything up. When you go through this thing, you basically can click on this button, and what it will do is it'll walk you through every single one of those little screens that tells you what you need to do to be able to do a design. Anytime you see something red, it means it needs input. Every time you see something yellow, it means there's input, but you might want to check it to be sure you're happy with it. And anytime it's green, it means you can do a design. Everywhere in this thing are basically what you saw on the screen. I simply put in length, area, anything that's yellow is calculated. I can say I want 1,000 square meters or whatever. I can change it from Yankee units to real ones, which is also nice. Don't laugh. I got to speak Yankee again. Most of my people are in the United States, and so it's like I got to think about like, oh, how many million psi is that? Damned if I know. I know it's 5,000 MPa. What the heck? So now I learned how to multiply by 145 and calculate it again. It's very frustrating. Yeah, I don't know what the hell's the matter with those people. Anyhow, well, actually, I do know what's the matter with those people. No, we don't need to go there. Right? I don't have time. Right. So this thing here is a description of what your surrounding area is here. So field, I can put in a contributing area. It's 500 square meters. I can calculate something. This curve number thing simply means what kind of surface is it that your contributing area is. And so I'm just going to say it's an impervious area, a parking lot. This number, curve number, 98, means 98% of the water that hits it's going to run off. So actually, let's not do that. Let's pick a golf course. So this is grass. Basically, 50% of the water that's going to hit that grass is going to run off. Right? So I picked that. And then I have a roughness coefficient, which basically is what kind of a surface it is. It's grass, so it's the roughness.
Sorry, can you just stop there?
Yeah.
Roughness coefficient, is that like a runoff coefficient?
Yeah.
And where did you get that data from? Have you done testing to get that data?
Yeah, and this actually comes from a big U.S. publication, actually, too. All of this stuff and if you do that, actually, probably here, let's check it out. Maybe I'm lying to you, but let me see what happens when I do this. There. There's a help menu in here. So this is made for anybody and anyone that wants to know anything about. There's the runoff coefficient, curve number. I guess I didn't have some of them's got references and things in there where you can find it all, right? So wherever you are, I just hit the F1 button and it brings you help from where you are to tell you about what's going on. Also, typically, like something like this, you can hover over things and it will tell you what it means. Because if you don't understand what it means, you can, read. Well, believe me, no disrespect, but I'm used to dealing with engineers, so I'm starting to learn how to speak architect too. It's harder than German, you know that? Really, architects. It is true. German's easier, than architects speak. Okay. So so pavement geometry here, it says, well, you actually entered a number, that's why these are yellow. If I would have said something like, 100 by 10 meters or something, and it would just calculate it, the number and the yellow things go away. So then we get into our subgrade layer. We've got a bunch of defaults here. These are all my defaults. It says for each of these different kinds of soils, you have something. If you don't like that, you want your own soil type called Dave, I can go through here and I can put numbers in and tell you what that soil type is, kind of stuff, and save it, and it'll always be in my records there for forever now. So I've got Dave in there. So whatever your soils are, I can delete it too, obviously. My wife would like to delete Dave some days, but that's another story as well. Anyway, so that's soil type. Let's not use Dave. Let's use something like clay. And so it gives you a bunch of calculations that are used in the program. The granular layers, you can decide if you are going to have in other words, if I was doing your design, I would do this, and it would all be the same material. There would be no base. It would be all our sub-base, but it would be your base. So we can just get rid of it, and that's all that happens. The choke criteria basically is if you've got multiple layers, I showed you that, if it doesn't want to fall into the layer beside it. So then we also have a gradation of the base. In this case, you build up whatever names you want in your own database. These are just the defaults from the program. We have the gradation of the material, the strength of the material, the porosity of the material is calculated based on density and specific gravity, etc., and it calculates numbers. It tells you what the permeability is going to be. Paving layer, you've seen this already. What's in that paving layer, including the bedding chip. This is the parameters for the bedding layer. And then in traffic side of things, basically we've got, we pick if it's a roadway, gives you all these things it wants to know. If you pick a parking area, and I said it wants to be cars and occasionally heavy vehicles, we just tell you should design for 75,000 easels. So then we get the structural design, and I'm already in traffic, sorry. The design parameters, we don't want you to touch them. If it's a white background, it means it's a default. If it's a yellow background, it's calculated. Structural base thickness, these are all the calculations you saw there earlier. And then in precipitation, we can go along and decide where we are. So I can go to here and change this. We've got US, Canada, and now New Zealand, and I can pick wherever, Otago or Otago? Otago, okay. So I can pick Dunedin, and it says this is what's from, and correct me where this is from. This is Niwa, okay, N-E-W-A, Niwa? Okay, so that's where I got all this data from. And so then Dave, I did this and sent it to Dave, and he comes back and he says, yeah, Niwa's great, except you know what, Auckland's different. So he gave me the numbers for Auckland. That sounds so familiar. I'm designing over there, and you tell me it's 100, and then here, no, it's 150. And there's this plexiglass wall between, and it doesn't rain differently, and that's what I was thinking about when you told me about Auckland. And then I saw the numbers and went, holy crap. So that's the plus 2 degrees C numbers, right? So I can pick those. I can pick whatever storm pattern I want, basically for what it fits. But right now we've picked TP108, and then I basically do a design. And I won't go through this thing here. I'm just going to pull up now, instead of showing you that, just quickly pull up Auckland, one that I did for Auckland. It's got a database. It saves all the data. I can take that data and I can export it. I can send it to him to go look at if he wants to look at what the same data is. A whole bunch of those basic features here, so I don't really have time to go into all of them in any great degree. So this is Auckland. I've just picked some basic parameters and some under drain pipes, etc. And so based on the storm events, my traffic here was 600,000 easels, so quite a bit of traffic. And basically based on the thickness that is provided for that base, which is 450 millimeters of sub-base and 100 of base, so 550 millimeters is only good for a storm design for 16 years. So now you said, well, I don't want a 16-year design, I want a 25-year design. So I go and I click this to 25 years, and if you saw down here, this number started changing, right? Or I can say, no, you know what, guys, I want it to be a 75-year storm, so I grab that, and it just went to 684. So it's interactive, and you can also make it automatic. So if I go down here and I click on this guy, real-time simulation, every time I change something in here, it's going to recalculate. I've also told it that you can't build 684 millimeters, so round it up to the next solid number. And so in this case, if I put 800 millimeters here in Auckland, it's good for an 85-year design storm for this particular one. Yes?
Sorry, Dave, when you get into depths like that, obviously you said anything beyond, say, 500 mils, mostly. So that's your storage.
That's storage only. Yeah, that's storage. That's not traffic related. So actually, if I go look at this, it says you need 74 millimeters for strength. You're giving me 90 now. This is storage numbers. So what I learned from this was like, wow, that's a huge difference between the two.
So are you storing a whole storm?
No, this is actually this is for 24 hours, basically. So my criteria, I had to decide what my criteria was for my design, which is water flow. I'm going over a 2-year design period. I can go 7 days. I can change all of this stuff, basically, to be 50% of the water gets out of the base, and I can go like this, and it'll recalculate all kinds of stuff here and tell you. This graph here tells me how much water's in the base, and it will be 50% empty by the end of 22 hours for the 2, 5, and 10-year storm. For the 25-year storm, it's going to take you 40 hours. For the 50-year storm, it's going to take you whatever 65, and it's going to be half empty at the end of 80, kind of thing. So this is just for getting rid of basically all the water within 24 hours. So there's a lot of little things. There's a lot of neat little things you can do to change all this. There is a setup file up here, the default values, that everything that I decided was default, you can change and save them. And so if you don't like what's there, you can make your own. Like I said that, for example, that the category 1 default is 7,500 easels for cars only, 30,000 for cars and occasional heavy vehicles, and and the other one was for the higher level, so I could change these numbers, and then the program uses them all. And so there's a lot of stuff you can change, or you can reset it to the factory values, basically. So it's not a lot of time here to be able to tell you all the little nuances and stuff with this, but it's and then the AutoCAD stuff. So at the end of the day, I go click here. My pavement structure that it designed, which was 700 millimeters thick, right, 700 and 100, that's the actual thickness of that layer. There it is there, 700. If I said it was 300, we'll resize and redo the drawing, basically, to tell you what it is, so you can copy and paste that into your drawings. Because, you know, people want to make it easy, right? So that's why we did that. The use of a geotextile or under drain, I can remove things and put them in and out. There's actually a space here, so there's case there's no under drain. I got rid of the under drain, now I put the under drain back. There is a place in the subgrade here, where is it? No, it's here, where I can actually say that I'm using a geotextile or a geomembrane. So if I use a geomembrane, it says no water gets into the ground. So I'll simulate all the calculations with no water getting into the ground. Anyway, so that's, I better shut up now, or he's not going to have a break. So bottom line is it's intended to be intuitively simple. And so I would expect, if I spent an hour with every one of you guys in this room here, you could all do this piece of cake. I mean, there's no reason why you can't do certainly a preliminary design anyway. In conjunction with that new standard, we also have all kinds of drawings and things like that, or if you're building it next to a wall, if you're building it on a slope, if you're, all different kinds of applications for it. So there's a lot more details that are available to you for doing design. We're trying to make it simple. Go ahead.
If you had this in New Zealand, have you asked them if you'll accept it?
Well, we kind of chatted a little bit about that yesterday.
One of the Auckland transporters.
Yeah, so does that have to be approved? Or?
I would expect it would. I would expect they'd have to look at it and decide. So in other agencies, a lot of them, this is designed for the masses. Okay, so this was what we.
What was the question again?
So the question is if you're using this, would it be accepted in New Zealand by the agencies? And so the answer was, well, I'm sure they would have to review it and make sure they're happy with it. From what I've seen and researched before getting here in our discussion yesterday, I'd say it meets almost all of the requirements that you normally have in your current system anyway. And so we made it for the masses because most people do it this way. Some don't. Some do it based on a 2-hour storm. So we've got a list of things that we've heard over the years that we might want to change. So if there was, 50 agencies that wanted something, we just make it happen ultimately, because we have control over the software. But for the most part, when people start doing this, it's reasonable. If you're a serious hydrologist, if you really want to get into all of the details and stuff in here on the, how the calculations are done and how the distributions are done and all of this stuff, and, all the equations are in here someplace as well, under hydrologic analysis. These are all the calculations. So it tells you everything about how you do it. So if you don't like it, then something else could be done, certainly. But the way it's done is completely open. So there's nothing hidden. There's no black box. There's no nothing.
One thing that you might want to mention is that since we've been talking with David Hein over the last 6 months or so, we have had a copy of this, and we also have met with the Auckland Council with this software, and they actually have a copy of it too. So it'll just be a matter of time when they will become more.
There's 5,000 plus copies of this out in the world right now, and it's not just like it was built for North America, but mind you, there's lots of other people that are already using it the way they are. Oh, and like if you don't like this storm stuff here, you can literally go in here and add your own. I mean, so bottom line is I can add one, do it myself. So people are doing this, and because I was coming to visit with you guys, I thought, well, you know what, I'm going to show you that I can do this really easy. And so I wouldn't want you to do this. I mean, I would just do the rest of the country. That's just tell me what cities you want it for, and we do the whole country, because it's simple once you start doing it. So it's no big deal. Oh, sorry, I hit something. He's going to hate me for that, I know.
Is it just for concrete pavers or is it for previous concrete?
You can use this for actually asphalt or pavers or brick. In terms of pervious concrete, it's a different design process. So it's using flexural strength, and there's other software that can do that. And also, you can honestly, most people have got some spreadsheets or something you can use for things. Again, we wanted to have it something that's simple, that people can easily do it and combine both at the same time. So you're doing structural and hydrologic design at the same
Sorry,
time.
Dave, with the previous concrete, are you suggesting that the pervious wearing layer actually contributes to the structural integrity of the pavement?
Yes.
Oh.
Yes, but so the thing is that I could do it with this because the hydrology is the same. So I can make this. I could do the same kind of thing with this actually for pervious concrete.
So have you done flexural tensile tests on pervious concrete?
Yeah, we have. Yeah, I mean it's all about the flexural strength of the pervious concrete, really, and it's not the people want to know about compressive strength and things like that. With concrete, it's all about flexural strength. Compressive means nothing to me. So if you core it and you want compressive strength, I want to know what flexural is. It's difficult. A no-fines concrete is very difficult to categorize. So many other things. You can have a perfectly good, dense, well-compacted, pervious concrete that's going to last, but it may not have the numbers that you normally would associate with concrete pavements. And so the industry, and at least in North America, they waffle a lot about it. They just waffle. And so, like the pavement cross-section you've seen out here that Steve put out there, is cool. I really like that one because that's one where I need strength. I'm going to put the pervious concrete under the pavers because we have a lot of problem with turning tires and stuff like that, and so I want a solid surface. So I work for all the industries, everyone, so in the same thing, but the one that has the most challenges is pervious concrete surfaced permeable pavements. So ones that have concrete on the surface. It's all about making it, building it right. It's construction. You've got to have the cement hydrate. You can't do it on a sunny day with wind going like crazy, or you're not going to get the cement to hydrate to make the glue stick. So it's more about the construction. And it is like baking a cake rather than eating a steak on a barbecue. You have to be right just with the parameters. So he's kicking me off now.
Yeah, I think you did fantastic. You did a 3-hour presentation.
Sorry, I talked way too fast, but that's all you gave me, so that's what I had. So there you go.
Okay, so it's 3 o'clock now, so we have a little tea break until 3:15, and then we are back here to hear Sam Blackburn's presentation. Thank you so much.